Back, everyone. So we heard a very interesting talk from Professor Moty Heiblum yesterday, and today we'll heard more interesting results from him on topological thermal Hall conductance of even denominator fractional states. So welcome, Professor Heiblum.
That's the one. Okay, before I come and talk to you about this work that lasted for about 5 years, and I'll tell you why it lasted for so long and how many experiments we did. Just before this, I just want to say a couple of statements that has to do with this work. I am also an American citizen. I grew up in Israel. I had my BSc in electrical engineering, and I studied in the United States, in Berkeley, in Carnegie Mellon, and finally in IBM Research Center. So I owe to this country a lot. This country made me what I am as a scientist. In 1990, I came back to Israel, and with the knowledge that I acquired, I built a research center that by some luck, the missiles that came from Iran missed it, just by about 200 meters. So the institute that I am now a part of, the Weizman Institute, is in great pain, and it will take some time to recover. 5 to 7 years is $1 billion or so, which is a lot of money in Israel. So the other point I want to say, that Israel and the United States are on the same path, going downhill. Okay. The state of the United States and Israel, being fully democratic states, are rolling down to a very dangerous place. And the reason I say it, because the United States is also part of me. I've been here many, many times. And it's difficult for me to see the destruction of the country economically and scientifically. I walk around the campus here, this beautiful campus. Will it contain so beautiful in the past? Will it be supported? It's very worrisome, and the same thing we have in Israel too, that lots of the money goes to the war that we continue now for the last third year. So there are leaders that make decisions for millions of people. And that's the democratic system. So I had to say something because I'm saddened by what's going on here and in Israel too. And I think what makes me somehow not totally upset is burying myself in my science. Okay, so now I'll tell you about, and I stand here that I can see this, about work that started and continued. And the continuation was because the theorists did not like the results. This is very upsetting. But now they do. Okay, so I want to tell you about this thermal transport. What I told you before was transport, right? Fractional charge, noise, particle, interference. Okay. We moved around charge in edge modes. But as you will see, this is not enough because there are edge modes that are chargeless. We call it neutron modes. And then you don't see them. They're just there. So when both of them, the charge mode and the neutron mode, carries energy, you can measure transport of energy, which is more difficult because energy can just fly around somewhere. Edge mode stays around, but energy can just dissipate somewhere. So you have to be You have to find a way to do it. And what I'm going to describe to you in the following hour or so is type of experiments that we did to try to prove that we see a non-abelian state that was for a long time a theoretical projection. And just stop me if I say something unclear. Okay, so if you just look on this simple, matrix multiplication, which I use only a very simple part of it, because we have in our electron hole, in our system, we have an electron hole symmetry, so I can remove this part, Seebeck effect, effect, not effective at all. And then what you see, we have an electrical current, okay, which is charge versus time, change of charge versus time. And then the heat current is energy versus time, okay? And you will see this kappa always, okay? And delta T always. Okay, so it started basically, at least for us, really we copied work done by the French group, by Frédéric Pierre. It was 2012, okay, that used this idea to measure integer modes, okay, and we just expanded it more. Okay, so Pendry did something else, okay? What Pendry did is an Englishman. He did this work, he found out that there is, if you have a single edge mode, non-interacting edge mode of no matter what, phonon, electrons, whatever you, photons, there is some limit of information that they can carry instead. One dimension I'm talking about, okay? But the way he did it, and you can find this paper, I think he wrote in 1984, if I remember right, 1983, yeah. So he just calculate the information transfer, and then from that the entropy, and from entropy you go to thermal energy. Okay. So the upper limit, he said that there is an upper limit, and the upper limit is this kappa zero, this magical number, which I didn't know before, that there is this universal number that we call kappa zero. Okay, you will see in a second what it is. Okay, so this kappa zero is contained this fundamental constant. Okay, there is pi, Boltzmann, Planck. That's all. No charge. Okay, so no charge because also photon carries energy. Okay, or whatever. Okay, so this equals I'm supposed to be. This is the number in watts per Kelvin square, and that's the way you look at it. The derivative of heat moving in time is kappa zero t, and you will see how it evolves. So if you want to find out the heat current, then you basically take a hot source, you heat it up relative to a cold one, and you find out how much heat energy moved from the hot to the cold. Okay. So again, the expansion later on, and you see here in 1997 was by Kane and Fisher that suggested that not only you have kappa zero that carries electrons, or what he did for photons, but it applies also to fractional charges. Not a billion, okay? And they get examples of 1/3 and 1/5, 1/7. So 1/3 carry the same amount of charge of heat as 1. Because everything moves forward, okay, and the calculation is quite involved. Not this is the only one that did the calculation, but they found the same upper limit of this kappa zero per channel. Okay, so the interaction somehow does not affect, right? 1/3 is just because of the interaction of electrons. So the interaction doesn't stop you from carrying energy in a one-dimensional channel. Okay, so let's go back to what we talked before. I think there are some repetition here and there, that the bulk hosts quasi-particles. So there is electrons, okay, there are electrons there, and there are fractional charges, and there are neutral modes that I showed you before. Maybe I'll show again. 1/3, okay, and then there are quasi-particles, okay, and then the abelians are these Laplace states, okay, all of them is on the denominator, and the non-abelian is half, 5/2, and some say that this is the 12-fifths, okay, which they call the parafermion, which is a fraction of the Majorana, which is another step up. We try very hard to try to measure this, but the 12-fifths is a tiny energy gap, maybe about 20 millikelvin or so. We just couldn't see. We couldn't see this way. I'm still not giving up. Because it would be nice to find a fractional from marijuana. At least it's theoretical. So just to remind you, because neutral mode will be all over the place, because the marijuana will be also neutral. So I'm just reminding you the 2/3. The 2/3, what we call now electron-hole conjugated state. Okay, so it's like I told you yesterday, I think, it's like what Alan McDonald said. Okay, that you basically have a full Landau level of electrons, and you have 1/3 of holes sitting inside, and as a result, you have an electron going one way, and 1/3 goes in the opposite. Okay. But this one, maybe we made an experiment to prove that a very, very short distance is indeed takes the place. But other than this, there is interaction between them. There is carrier move from one place to another, and eventually you get downstream a charge, an edge mode that is 2e over 3, okay? And it goes upstream, okay? The neutral goes upstream, and the 2/3 go downstream, and the neutral goes upstream. So now it's more complicated. So when you have now edge mode that goes around there, the neutral are going opposite. And they're very important. They have a lot of jobs. Okay. So neutral mode, again, they are what's obvious to you now. It's invisible, right? You don't see it in conductance measurement. It is visible, but you do noise measurement. Okay, so the way that we discovered the neutral mode way back, okay, I think it was about 15 to 20 years back, we were looking for it. This neutral mode are not photons. They are electron hole pair, okay, that are jumping around in time like this, and you see something which is an average. And if you come now to an ohmic contact in front of an amplifier, you can see this noise. You can measure this noise. So we measure the neutral mode. We can measure it by thermal transform, but we detect them also just by measuring noise. Okay. It's like a short noise, but it doesn't tell you anything about the charge, just the presence of this neutral mode. And they can be bosonic, okay? They're in these 2/3 are bosonic. And then they can be non-abelian, which is MI1. We'll come to it, which is very important. Okay, and then the other point is about edge mode is topological and non-topological. What do I mean by non-topological? Suppose I measure something. We have edge mode, edge bulk edge correspondence, right? So there's some correspondence between the edge mode that goes around the bulk, okay? The edge mode knows something about the bulk. But sometimes, and this tells you that's what we do, we measure only heat going through the edge mode. We have an experiment also heat goes through the bulk, but that's another paper that we're not going to talk about because the bulk is not infinite resistance to the energy, but we measure everything on the edge mode and we know something about the wave function in the bulk. Okay, but sometimes the edge mode is funny because there is some reconstruction. Suppose now the carrier density goes down, right? You had the whole bulk is finished here. Density goes down, and then the system prefers now, rather than to go down all the time and have this kinetic energy, to have another step, at 1/3. You have sort of an incompressible state of one, and you lower this way the kinetic energy in the system. And if you do it, then the edge is reconstructed. The edge becomes funnier, okay? But if you are now going and say, oh, how can I measure now the thermal transfer because I have another non-topological edge there? Well, you don't because all this stuff that edits in are going this way back because they cancel each other. So luckily enough, you have to be careful to measure non-topological systems in an edge mode and measure basically topological that will tell you the wave function in the bulk. Okay, so I showed you this picture before this bubble of the hotspot. And why do I show it again? Because if you want now to energize the neutron, you cannot put voltage. You have to put heat, right? So where do you get the heat? Okay, so when you have now a current goes to the ohmic contact, so current comes down at the voltage and energy EV, and the contact is grounded, something like this, okay? It's low. So now it loses its energy. From EV goes down to 0 into the hotspot. Okay, it loses energy at the entrance to the metal. If the metal is tiny, the whole metal can be hot. If the metal is big, ohmic contact is large, it's only a hot spot. And this is this hot spot that I wrote down there. And this hot spot is the source of energy to neutral mode, to marijuana, to neutral mode everywhere. So if you want to excite a neutral mode, it has to come from the hotspot. Okay? So here, if there is a neutral mode, it takes this energy and moves on. Just as an example, let's say if it's 2/3, this blue dotted line or something like this, a wiggly line will carry energy from the hotspot. Okay, so this is kind of an introduction to what I'm going to do later. Okay, so now let's look now. So the bulk has localized states. Okay, the localized states indicate some vortices in the bulk. Okay, that's this order there. There are also loops that goes around in this order. The current goes around them, and the current goes over the bulk. Depends how clean is the bulk itself, but ideally it is insulated. Okay, there is some RxX. If you want to make Hall effect, right? Many of you do measure Hall effect, right? And you want to know what is the bulk resistance. So if you do Rxy squared divided by Rxx, that's the bulk resistance, dot square. Because if you know 10 ohm, it doesn't tell you much about the bulk. It has to be, you have to know Rxy and Rxx. But this is not so important now, okay? Okay, so you have now this bulk, localized quasi-particle. Then we have now integer edge modes, okay, 1, 2, 3, 4, all these things that you know by heart. And then at the edge mode, okay, we have these fractional 1D chiral channels. They could be a billion, I repeat the same number again, and they can be also neutral mode. They can be 5/2 and 7/2. That's what I want to show you also. Talk to the bulk because this is all the experiment that we do will lead to this 5/2 and 7/2. Okay, so again, these are all the edge mode that you can think about, right? There is regular edge mode, 3/1, something like this, chiral edge mode. Okay? And then you have also mixed up, you have down and up neutral, for example, the electron hole conjugated state, and the non-abelian. Non-abelian one, you might have current, half, let's say, of the 5/2, and you have a neutral mode going back, and presumably it's a marijuana. Okay, so the thermal conductors, what's so fantastic because it is sensitive to all energy, to all edge modes, okay? So it's providing also it provided the topological order. Namely, as you see, what do I mean by topological order? Because if you have 5/2, you can have something like 12 versions of 5/2. The 5/2 can be, there are like 4 versions of a billion 5/2, and there are some 9, if I recall, of non-abelian. Okay, and the question is, CEOs calculate, right? They like to calculate stuff, and they project something between five. Okay, so again, the Pendry general theory moves now again to Kane Fisher and also to Kitchener. Then we talk about now basically Dieterman Franz breaks down because now before, if you have all of the electrodes, there is this Lorentz number, which is the ratio between the conductance and the thermal conductance. But now we need 1/3 suddenly, then it breaks down. Okay, so interaction should not affect now the thermal conductance of what I say of kappa 0. This interaction, it's a repeat what I say about fractional charge. Okay, so now the past experiment before we did the experiment, okay? Before we did the experiment, then there were published papers about measuring this kappa 0 per mode, and this particular one was 16 mode. I think this was in Caltech. This one I remember where it was in Europe somewhere, photon, and this one is the one that we copied. It was what I told you that the work that was done in France. Okay. Okay, so we took his idea, which I will show you now, and we expanded it. Okay, so here is again something about the topological order. So it determined the topological order basically, it's another word for the wave function. Okay, so because of bulk edge correspondence, but the edge also I learned is not the edge itself, it's everything that goes along the edge. It can be a bunch of edge mode that goes. So everything that goes along the edge tells you something about the bulk. And then you have here that you can reveal, the net chirality of the mode, okay? In equilibrium, you have downstream and upstream. And the point is that when you have this mode going back and forth and you do this measurement, which I'll show you, The question is, do they equilibrate on the way, or they just ignore each other? That's very important, okay? Because if you have an edge go down and another edge goes up, and it's totally cold, and this is hot, nothing comes back. But in the disturbance equilibration, some comes back too. So this makes life more complicated, okay? So you need to go initially at least, I'll show you, we start with very long propagation lengths, and then we went to very short propagation length. We didn't want any equilibration at all. So these are all the tests that we did. So then you have this independent edge reconstruction, but the topological order is independent of edge reconstruction if it's long. Okay. So now, I showed you before about half and 5-half. We say a few words. I'm not going to talk much about it at all. But in a way, you have these not a billion states, and they can have a Majorana, or they can have fractional Majorana. Now they call it fermions or so. And maybe in the future, in all kinds of TMDs and field, etc., that are more resilient to high temperature, we work at 10 millikelvin. But in graphene, you can work at 100 millikelvin and even more, because the gaps are much bigger than in gallium arsenide. This is all gallium arsenide, right? So we do gallium arsenide, okay? So in a way, also in a wire, Kitaev had this wire, which we also made experiment, and you know that the Majorana stuff blew up now. Nobody wants to talk about Majorana in wires, right? And then you have a Majorana sitting on this side and this side, and these two Majoranas are half a fermion each of them. Okay, so the kappa that you are going to measure, the coefficient, thermal coefficient, has to do with how many charge mode or neutral mode are there, which are kappa times 0, kappa 0 times n, I'm sorry, and you have also another half, if it's 1/2. For example, there are topological order, like if I say now, you'll see it later, in anti-Paffiard, that has 3 Majorans. Okay? But in order to have non-abelian, you always have to have odd numbers. Because if you have 2 numbers, it becomes like a wave electron by fermion. Okay, so here, so what you do is when you can measure now this thermal conductance, you have photons, phonons, electrons, abelian, neutral, all of them are kappa 0. Okay? That's magical, right? With 1D. And then you have this non-abelian one, okay, that is a fractional. This coefficient now, this G, it's a fractional one. Namely, it's not kappa 0, but it is smaller than kappa 0. It's half kappa 0. A regular Majorana is half kappa 0. That's what we were looking for. So just to measure the thermal conductance, and you see this half kappa 0 sitting there, then you find new level about non-abelian state. You can also, there are many proposals to do interference of this 5-half. And we are also slaving with it, but it doesn't work so easily. Okay? But no one showed yet interference of 5-half. There are projection, there are theory that you change the magnetic field, and sometimes you have interference and you don't, and you do and you don't. But no one yet measured it, but I'm sure it will happen soon. Yes.
Can I ask a quick question about
Yes.
phonons? So
About donors?
Phonons.
Phonons.
So understand from the perspective of 1D transport that you will have an integer C from
A line of phonons.
Yeah.
Yeah.
So, but if the quantum Hall system, you have probably gamma phonons that are 2D. So in this case, it doesn't seem like it will contribute a quantized thermal Hall, right?
That's
so
true.
Can you comment a bit on that? That may ruin your 0.5 quantized thing from 1 billion, right?
Well, it depends, okay? If you say now that you have phonons sitting in the bulk, okay? In general, at very low temperature, this phonon totally freeze up. The issue that you're going to get, as I'll show, that the ohmic contact that I heat up as a source of heat, that I want this heat to go to the edge mode, part of it goes to phonons also. That's a problem. So we have to get, and this is depending on temperature to the power 5. Then what we do is we go to very low temperature to kill it, or I'll show you how, in one example, how we get rid of them in the calculation. So I'm not talking about phonons in the bulk at super low temperature of 10 millikelvin. Okay? Maybe they are there, but they are not excited. Okay. Okay, so again, you see this beautiful stuff, okay, this number again, and I showed it again, a billion charge, okay, a reminder. And now I'm going to the very first experiment. And we had many students that were working, okay, from 2017 until today, until last year. And I'm not going to mention all the name and all the paper, it was this, the area nature stuff. I just want to mention Mitali Banerjee, if you know the name, because she was my postdoc. And she pushed me to do this experiment. Okay? And I don't think if she would be there, if she didn't push me to do it, I might not be doing it. So I think I recognize her by this name. She made 2 experiments, okay, 2 papers, 2 major papers. And this started basically the rollout of our work. Okay, now she's a professor in EPFL in Lausanne, in Switzerland. Okay. So regarding now the simple experiment, you take a reservoir, you heat it up, okay, not with a candle, and you let now some heat going through an edge mode, that's an edge mode, okay, to a cold reservoir, and also there are phonons. You see, this is 2 to the 5th, there are phonons. And it depends if your reservoir is very large, then you have other phonons. So if you want to make it small, relative, it will be hot for an edge mode, it's okay, but you want to minimize the amount of phonons that will take heat out of the system. Okay. So that's what I wrote down here is exactly what I'm saying now, that this is the current that will go here, or the heat current that goes to this edge mode, and plus there is some heat that will dissipate so the phonons. Okay, and this one I wrote here is 1 dimension because this is the edge, okay, or many edge, okay. So the downstream leaves the source, okay, and the upstream that goes there comes back. It comes on the ground. Okay, so you have to think about it. Also, the ground, if the ground is very far away, still you have a hotspot, right? Because you come with voltage, falls down, you have a hotspot, and if there is neutral mode, then basically it will be heat up, start moving back, and then it can, equilibrate with this mode that is going there. Let's say if you have 2/3, 2/3 is a beautiful example that I'll talk about in class. 2/3 goes down, kappa 0. The neutral mode of the 2/3 come back, kappa 0. Long enough, they cancel each other, they equilibrate, and no heat is going on. All the heat that you send out will come back. Okay, so I'll show you this example. Okay, so the first experiment that we did, okay, is to measure this kappa 2 terminal. And the kappa 2 terminal here, the kappa 2 terminal, we want it to be kappa xy. So if you have full thermal equilibration, then we know. Then, for example, we'll see in a second, 2/3, the kappa is 0. Namely, if ideally, if everything comes back, we start warming up, and it will explode. The temperature will go up forever. Because everything that we leave will come back. And I'm not talking about phonons now, it doesn't matter. Okay? So this kappa 2 terminal was the first work that we started with. Okay? It was not the topological number, is the kappa xy. Okay, this is topological kappa. Okay, so here an example, and this is also taken from Kevin Fisher. Okay, so for example, 1/3, what he wrote down, 1/3 kappa 0. It's the same as electrons. Okay, and this is 2/5. There are 2 modes. It's 1/3 and 1/15. Okay, so these 2 modes are going around, and you have 2 kappa 0, which we measure, but I'm not going to show you all the measurement of all the state that we measure. Okay, but this is kappa equal to 0. 2/3, I'll give an example, is 0, because there is 1 down and 1 up. Okay, and this is now a neutral, and this is now a charge, and both of them carry kappa 0. And if you have infinite distance, then it will be 0. The kappa will be 0. And maybe it's difficult to see it, but I'll show you an example. But now, if you have now this other conjugated state, which is 3/5, then you have now 2 neutral modes going up and 1 down. It is very strange because because the current goes in one direction, but the heat goes in the opposite direction. And then we measure it, okay? So it's kind of cute, no? Heat goes this way and charge goes this way. Okay. So this is sort of like an example of the two cells that I want to talk about now. Just to give you an example. So here is the two cell that you have now two cells in neutral going back. And now what happens is, suppose now I made this pictorial picture. So you have now this hot source, okay? And the hot source now, it's difficult to see arrows, okay? But you have here charge that goes, this is chirality. So charge goes down here, okay? If it goes down here, and then my marijuana goes from the heat, it's hot, right? It's not even hot spot, goes the other way around. Okay, and now it is very long, okay? And now, so you have now what I wrote down here, that hot two cell mode go in this direction, okay? In the opposite direction, you have hot two cell goes in the opposite direction because it comes up from this hot source. Because I heat up the hot source to TM, okay? But now don't forget the other two modes, okay? So this now cold mode comes back. I mean, all mode, the neutral goes this way and the edge goes this way, but they always come back. Okay. So now you have the cold upstream mode going in the opposite direction, okay? And you have also the cold charge mode going in the opposite direction. And if now they thermally equilibrate, everything comes back. Okay? So nothing leaves. So kappa is supposed to be 0. And the temperature will climb up. Of course, the phonons, the bulk phonons, everything will stop it, and it's not be the case. But ideally, you understand that kappa is supposed to be 0 for two cells. And you will see that it's not easy. It's easy to see the 0, and I'll show you toward the end of the talk that we got the 0. Okay, so that's exactly what I wrote down there. Okay, so if now suppose there is no at all equilibration, 0 equilibration. So the kappa is 2, because the charge goes this way, the neutron go this way, they never go back. They don't equilibrate with other, so you go from 2 to 0, right? 2H mode goes up and not seeing anything else in the world. So kappa is 2. So you have always to understand that you get something between 0 and 2. And when we measure the intensity in a second, we never get here the 0. It's very difficult to get the 0. Okay, so the experiment that we do is, again, we take now a hot OMI contact, I'll show you how it looks like, and we heat it up. And the way that we heat it up, I don't know the time, just oh, I'm supposed to stop when? 2:30? Oh, okay. So you went to heat it up. So you come from a source with a current, and then you get now, let's say, you have now one edge mode, single edge mode, okay? It comes down here and comes down here. This is a 2 edge mode. So to get 2 edge mode, the voltage drops down to half, okay? Because the voltage is half. So now if you look at the power dissipation, it's P in that comes from here divided by 2. So you dissipate, and the more arms you have more of this dissipation in your OMI contact itself. As long as the current that comes in, everything equilibrates, and the temperature of the OMI contact is steady. And the OMI contact is small, okay? And again, here the first experiment that Mitali did was really to put a current in and have 4 arms. It looks like an arrow, but it's always the waveguide, sort of 2D. In the 2D, you have also current goes this way, and the ground something backs. But schematically, you have now 4-arm device. Okay? This is the first paper published in 2017. This was just regular, not 5F, etc. Okay. So in general, what you do, you want to know the temperature of your source. So how do you know the temperature of the source? So you have this amplifier that measures the Johnson-Nyquist noise. Okay, far away. So it doesn't matter because the frequency that we measure is something like about a megahertz or so. Okay. We measure the temperature, the frequency at 10 or 20 or 30 millikelvin goes all the way up to a few hundred megahertz, okay, frequency of the Johnson noise. So we measure it far away. We don't lose it at all. There's nothing to lose it. okay? We see it, we don't go far away, but 100 microns, okay? We see the temperature also of the source, the heated source, okay? So it's what I wrote down is distance independent. If you put it in a few places, we measure the same place. Because the low frequency current are conserved. They don't go anywhere. They are not coupled to capacitances around or anything like this. And when I say megahertz, this is for me low frequency. And it's an example when you measure now the noise, okay? When you measure now the noise, you're looking at only one side as a function of the current that they put into the flow of the contact, okay? Then you see how the temperature of the contact is increased. So I think that for all experiments in this area, very few are measuring droplets, determinants, 4 groups in the world. You should measure it. That's the way you measure the charge, you measure the temperature, and I don't know why. I think only the French group, 2 French groups are doing it. We are doing it in Israel. That's about it, maybe in this one. And I will teach everybody if you want how to measure it, okay? It's very simple. So the experiment, again, the very first experiment we did, we have this Omi contact, small Omi contact, it's about 40 microns square, okay? And we do, and below this, we make some cups, you don't see it below it, so the current goes into the gas, go to the contact and continues. Okay, so we heat up this contact, and then these are etched region here. This is filling factor 2, and there are here 8 edge groups, okay? And the only thing I said that there is only a gate here, we can block this particular, so you have here an arm goes this way, an arm goes this way, etc. And each arm length is about 150 microns. Okay? To guarantee thermalization, but it's not guaranteed. As you will see in 2/3, it's not guaranteed. Okay. So we can play with these gates and shut arms down, or partly short and filling factor 2, a particular edge mode out of the 2, etc. Okay, so what we do, how do you determine the thermal conductance? Okay, so first of all, you calculate the dissipated power. You know the dissipated power. Okay, you know also the temperature. Okay, you know the temperature. The floating reservoir, that's the only contact that I told you. Okay, if temperature is very, very large, then we have to subtract the formula. Okay, so we will usually go up to about 20 millikelvin or so. Okay, and stop there. But if you go much higher, phonon kicks out because it goes into the fifths. So I just want to show you this very, very quickly, right? We don't have to elaborate, so we can get the same temperature, okay, with different lines open. Okay, for example, if I have here Ni edge mode, oops, sorry. Oh, sorry. If I get here Ni and here Nj, different openings, different edge modes going on. But in all cases, the temperature of the floating contact is the same. Okay, so if right now this dissipation here and here, the phonon don't know if I have 1 arm, 2 arms, 3 arms. They know that there is a temperature here, and they come out from the floating contact because of temperature. So if I subtract these 2 equations, I got now something that has to do with subtracting of this thermal transport, and the phonon disappears. Okay, maybe you need to make it more. So all the time we subtract. Okay, what you see here is we say here, in this particular, we have filling factor 2, 4 arms, so we have 8 edge modes. Okay, and then we subtracted, for example, 8 minus 2. Okay, so we measure 8 of them, and then we measure only 2 of them and close the other one. And then you see all these as a function of temperature square. You have this equation there. It doesn't matter, but finally you find something aligned with this kappa is equal very close to 1 per mole. Okay, so this is just proving that every edge mode of electrons carries kappa 0. And now if I go to 1/3, and I'm not going to show you the 2/5, everything, I won't finish with everything, but the 1/3 is also 1, exactly what Kenneth Fisher predicted. It's also kappa 0. Okay. So fraction, abelian fraction is okay. Okay, and now we go now to the whole conjugated state, and this is to remind you how it looks like, okay? So here, when you go down, then you have now heat goes on the right side of the arm, and heat comes back on the other side. And if you do it 4/7, you can see right away that all this dotted line and full lines, each of them is kappa 0. Okay? So this particular one has -2, and we measure this -2. 3, 5, 5, we measure also -1. So, and when we go to 2/3, we don't measure 0, because you have only 2 of them. If you have 2 and 1 or 3 and 1, equilibration somehow takes place. If only 2, that's what we learned, it doesn't equilibrate. So we get only 2/3. And suffer. We tried also, so we increased temperature, and the 2/3 was when this number when with this number, which I'll show you the number. I think it's here. It got equilibrated. Is about I didn't write. It's about 0.35 instead of it's 0.35 kappa. Okay, kappa 0. And I'll show you in the later part how can we go over it and really measure the 0 of 2/3. But the 0 of the 2/3 is very, very difficult. Maybe I have to go to huge distance, more than 150 microns to get full equilibration. But at the same time, you might also lose temperature fluctuation and measure the temperature, etc. Anyhow, so point of consideration is exactly what I was saying here. Okay, so first of all, the only contact that you heat up, electron has to be terribly tiny, 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 because you have to heat it up. Okay, so all the electrons inside have to be equilibrated to a temperature. And then the temperature that goes out, Johnson-Nyquist noise, we measure it, okay? And we have to be very careful, because if your ohmic contact has some ohmic contact that is not 0, and there is some potential in it, it can create shocks. It's very difficult to make an ohmic contact that is connected to the edge mode, and it has 0 contact resistance. If you have a contact resistance, you create shock loss, because it's like a new barrier that, as I showed you yesterday, you have shock loss, also a barrier. So, so you have to be very, very careful in making tiny ohmic contact with very small contact resistance. And then we assume here that the bulk in this experiment is gapless, is gapped, and you don't have any thermal conductance with bulk, which is incorrect. Later on, we have the whole paper published in Nature that instead of sitting at the center of the plateau, we move to the right or to the left, and you see thermal conductance in the bulk. Okay, so puddles that are in the bulk, and each puddle have an edge mode goes around, and the edge mode talks to each other. Okay, not by conductance, but by thermal conductance. Okay? So one has to be careful if you want to measure stuff. You have to know that the bulk is also adding to the picture. Maybe not very much. And then length of the arm. So we use 150 micron, but if you want to use more than this, it's okay. And there are also experimentalists that are measuring in graphene, but they use only 10 microns. They don't have 150 microns in graphene. And their experiments now is limited in a way, in my opinion, because they don't have thermal equilibration at all in a very short piece of graphene. Okay, so this is just a joke coming in this topic. And here, I showed you this picture yesterday. Okay, this is the 5F. Okay, so you talk about now composite thermal liquid. Okay, and I'm jumping right away to the measurement of 5F. Okay, so here on the left, you see now the Hall effect of 5F, which is a reasonable picture. Okay, it took us a long time to get it, and I'll tell you why. Initially, there are few ways to dope gallium arsenide. Okay, you can put donors inside in aluminum gallium arsenide, and they freeze out. Okay, and you can put the dopant in quantum wells. Okay, so they are free to move inside, and the screening is fantastic, and you get very wide plateaus on the 5F and beautiful RXX sequence. But this doping, this electron in the dopant wells carry heat. So this carry heat at the top, on top of the 2D gas at the bottom. So we did it and got nonsense. So what did we do? Now we go and dope it not in this fantastic way, okay? That gives us fantastic 5F in conductance, okay? In conductance, you don't see these added electrons in the donor because they are sluggish, but the heat can go through. So here now the plateaus are small. They're about 300 or 400 Gauss rather than 1500 Gauss. Because we don't want to have any heat going through the donor state, okay, in parallel. Okay, so this is now, you can see there, okay, you can see here the 5/2, and then the two neighbors is 8/3 and 7/3 on both sides. Okay, so first, what are the projections? Okay, this table, when we start the experiment, we get this table. Okay, and the table tell you what is the possible topological orders of 2.5 and 5/2. Okay, so on the left side you have a billion. Okay, they could be totally a billion. All the resistance you can say here, it's a bit. Okay, you can see here this line, wiggly line, is a neutral. Okay, is a neutral. The thin line here is the quarter, is the half channel. And this set one is 1 and 2, two integer. So two integer, one fraction, one neutral. Okay? Okay. In this particular one is the half. There is no neutral at all. And there are neutral here going backward, forward, etc. Okay, so all these are abelian state, and they will give you a conductance of 5/2. Okay? A conductance. Not thermoconductors, but conductors. And here is the non-abelian one. Okay, and we'll come back to it again and again, and I'm sure that you'll be confused what happens because I'm showing you here a representation of 2.5 and a Majorana going back in this particular case. But you can also look at it as 3 and a minus charge going back. To get 2.5, you can get 3 minus half, or you can do 2 plus half. And we use these experiments by interfacing with 3 and interfacing with 2, as you can see in a bit. Okay, so the red line here is the antipathium. So there were many calculations, numerical calculation, suggested the bulk is antipathium. Okay? And if the bulk is antipathium, the kappa you can see here. Okay, so you can see 1, 2, okay, 3, okay, and there you have here minus 1 and minus half. So this is like 3 Majorana, which is 1.5. 1.5 kappa 0. We write the kappa 0. So the pH Paphian, I'm sorry, the antipathian, everybody was all the calculation before we start the measurement, everybody expect antipathian. Okay, so basically now, and then what do we do now? So the measurement that we did now, okay, harboring this Majorana. So this shows now the charge also that we measured before, and then these non-abelian anions. Okay, I just say something again about non-abelian. Let me see if I have the result. Yes, I have the result later. Okay, so when you move away from the B equal half, which is 2.5, etc., then you have all the time vortices that come in, and you can read what's written down here. This is just something to do with the details of the final. I don't want to spend time on this. It's very simple. The degeneracy of the ground state is 2 to the power n over half to the number of vortices there are. And this is again what I showed you before. So this is just a different Omni contact, okay? But again, 4 arms, okay? And we are testing here 7/3 and 8/3. That's the both sides of the 5/2. Okay, and we expect here a billion. Okay. So the measurement result indeed was a billion. We measure 7/3 is what? Is 2 and 1/3. All of them are 3 kappa 0. Okay. So we measure now. I'm not showing you all the measurement and data because we spend now a couple of hours out of this. And the 8/3 is again with the problematic 2 and 2/3. So we're supposed to get here 2, and this 0.2 is the measurement itself. This is this 2/3 that doesn't want to be 0 because the distance is not long enough. And the 5/2 is 2 plus half. So these are the results here, measuring now the 7/3, okay, that was 3 kappa 0. And this particular one here, the 8/3, even the not RX at 0, but it measured now a bit bigger, larger, the 2.5. And here you can see now the 2 and the one minus the neutral mode, etc. What you know from before. So the 2/3 we measured, and it was more when kappa is than 0. And here also it's bigger than 2. It was 2.3 or something like this. Okay. But when we go down to the thermal conductance at 5 up, and there are, you can look at the paper, there are many, many experiments there, many tests, different temperature, and whatever you have, we measure kappa over kappa 0, 2.5. Anybody remember the table? Was it an antipathian? Okay. So this was not an antipathian. Okay? So what we measure, and we even didn't know when we measure, we were really, so I don't know, kids. We didn't know. We started measuring and we got this number of 2.5. And Italy went over to, where was it? To Princeton. And she gave a talk. And Halperin was sitting there, and JJ and another Jane was sitting there, all these big shots. And we just showed this data. And they killed us. It was a very terrible event. Okay? And by the way, until 2 years ago, they still killed us. They still could kill. Anyhow, okay? But we do experiments, okay? So this, nobody liked this result. People like the 1.5 and not 2.5. Okay, and if now we measure it as a function of temperature, you can see that we get now a pH factor. Okay, and when we cool it down, then equilibration fails, and we couldn't go down below 12 millikelvin and so on. And we could see that the kappa goes up a little. And this was published in the paper. Okay, so we see pH factor unexpected. And what happened is that Steve Simon, okay, you see Steve Simon, he was the referee of one of the referees of the paper. Okay, so there were 4 referees, just some anecdote. So he decided to get out and say, "I'm Steve Simon. I'm not going to referee the paper anymore. I think I like it or so, but have another explanation." Okay. And but the paper was accepted and published. Okay. What he's saying, that he thinks that the marijuana is not fully equilibrated. So the marijuana not fully equilibrated now. If you now don't equilibrate all of them together, okay, what you do that instead of antipathian, this marijuana, the marijuana is going the opposite direction. On the other side of the arm, there is an arm and there is one goes to the other side, and everything is equilibrated. But if the marijuana doesn't equilibrate, it comes back. Okay, it comes back. And it looks now exactly this particular, it's difficult maybe to see, this arrow flips around to this side. So you say because there is non-equilibration of the marijuana, you measure 2.5, but it's supposed to be still antipathic. Okay, maybe you was right. Okay, maybe 150 micron length is not sufficient. Okay, so this time on, from this point on, okay. So all these numerics, and it didn't take into account all the thermal disorder that was there. Landau level mixing was not taken into the calculation, but still the theorists were sure, okay, that this is wrong, that we measure something not correct. So what do you do? What do you do? So you can say, okay, that's what we do. But we continue doing here from 2018, 3 more measurements until last year. Because it was of interest to see, why don't we get what they expect us to get? Okay. So I want to show you now, in the time that we left, 3 more experiments that are different from this kappa 2 terminal. Okay. The last one is measuring kappa XY, which was a more difficult experiment than the other ones. Do you have any questions until now, or this is all okay? So first of all, so let's see, we thought about, there is so many modes. We have 3 minus half, or 2 plus half, and a marijuana. So all these modes have to equilibrate, right? And there are many modes that equilibrate the temperature. So the idea was now, why don't we isolate the half mode? Okay? isolate the half mode. So there is only half and the marijuana, this way or this way, doesn't matter. Okay. So if we isolate it, it will be easier for this marijuana and the quarter charge to equilibrate. So how do we do it? Okay, so to gap, you want to gap out the integers, okay, and then you use thermal equilibration, as I said. We have only 2 modes, and then we may distinguish more easily the chirality. So here is not thermal constant anymore. This is just this experiment is just the chirality of the marijuana, and you will see what I mean. Okay, so you take now and you put nearby 5 half and 2. Okay, and you can do also 5 half and 3. Okay, which we did both. Okay, so here you see that when you put 5 half and 2, what is remaining now is only the fraction. Okay, so here is an example of 2 and 3. Okay, just an example. Okay, so you have your 2 and 3, and if they gap each other, okay, then you have one more. Okay, the 2 and the 2 gap each other, and the third one remains. So what did we do? Okay, so we have now, and you will see in a minute, that you have now just a line, just an edge line. Now we don't measure thermal transfer at all, just have an interface between these 2 or 3 and the 5 half. Okay, or the 7/3 or the 8/3. We did all this. Okay. So if you now do it, okay, you can now gap it with 2 and the 5 half, but it's not a 5 half. You can now change now. Okay, we change the gate voltage, and you change now. You have 7/3 minus half, 5 half minus 2, all of them, and the other way is 3 minus 5. Okay, so you can have now. You can see now the resistance of the edge. The line itself is a subtraction between these 2. Like I did 3 minus 2, and I got 1. Okay. Okay. So what we do now here is we go now not to very far distance, we go to very short distance, 30 microns, not 150 microns. So okay. So now the point is what I'm going to show here, that if you have here a source and you have a hot spot at the source, okay, then you have from here a marijuana, a hot, if you have marijuana here, it comes up and we can measure at the amplifier the hot marijuana. Okay, and why do we have here a hot spot? Because you have a charge coming from here to here. Okay, the cold charge, and this one sits at some high voltage, and you create here a hot spot. Okay, so always have to look. If you have a hot spot, then you know marijuana needs to be hot spot. Okay, if there's no hot spot, marijuana is not excited. Okay, so now we remove now the integer. So we take now 3 factor 3 at the top. We do it also 3 and 2. 3 factor 3 at the top. And these are the 2 possibilities, the pH Pfaffian and the anti-Pfaffian. And as I show you, you probably will be mixed up and forgetting exactly all the errors, how they go back and forth. Okay, so the anti-Pfaffian is this, okay, and the pH Pfaffian is this, in the representation of not 2 plus, but 3 minus. Okay, so if I go it now, I can see that after now interface, after interfacing now the 3 and the anti-Pfaffian and the 3 and the pH Pfaffian, that's the final picture that I have. Okay, so here it looks like this is the anti-Pfaffian. You have here minus, this is 1.5 in this direction, and this is 1 minus half. And the question is now, will they at all? I want to see if something moving there. So I'm not necessarily going to equilibrate. I want to see just the noise coming in, because the distance is only 30 microns. Okay, so so if I remove now, you can now make a very nice, because if this guy comes out from a homey contact here, which is hot, okay, then you see that immediately you see both of them are equilibrated. Both of them came from the same temperature. They're equilibrated. You don't need any distance to equilibrate. This particular one does not. Okay, so if you look now the half and the n, now 1.5, these are more, they are equilibrated to begin with. In case I show you now and continue. They leave the same source. Okay, so here it's again, this is, I know that this is a bit confusing, all this stuff. Okay, so I have now not 3 and 2, but I have now another one, 2 and 5 half, and I have 2 and 5 half, and here is the pH Parthian, and this is the anti-Parthian. So the anti-Parthian have the same story. You remember these 3 marijuana going in the left direction, okay, and this is the half, the half that goes this direction, and the pH Parthian looks like this, okay. So you have an upstream mode in both cases. That means you will use hotspot here, this amplifier. So I'm going to measure hotspot here, and I'm going to measure hotspot here. So there's no difference. I don't know how to distinguish if it's Parthian or anti-Parthian. Okay. So you cannot distinguish in this particular experiment if it's a Parthian or anti-Parthian, because you measure noise in both cases. But if you go to 3, you do 3 minus 5 half, not 2 minus this. Then you see something different. Okay, now here you have again, this is the pH Parthian. Okay, so you have a hot marijuana, you see here, moving from the hot spot. Because why do we have a hot spot? Because we have a charge moving in this direction. And here we have something that goes in the opposite direction at all. I don't see anything here at all. I'm not supposed to see here any noise in the amplifier. If it's an anti-Parthian. And we don't, we see noise, which is this. So this is not something quantitative. It just tells you now, this one of the 3 experiments that I'm showing you, this one, suggests right away in a simple experiment, okay, that we see here in this particular configuration of pH Parthian, and not anti-Parthian. Okay, second experiment. The second experiment is again measuring what we Tali measured in 4 arms, but we measure now only in 2 arms. Okay. So measuring 2 arms, this is another device. Okay, it's 2 arms. This is a hot contact. It sends hot edge mode here and hot edge mode here. Okay. And you have in the opposite direction, this is upstream and downstream, okay, for this. Okay. And the downstream mode is the bottom mode. And then we want to measure now the thermal conductance, this particular one. It's only two arms, not 4 arms. Okay. So what you do, you play initially. So you have now a gate. I'm sorry, I didn't show you. So you have a gate. You see V. Okay. This is the new out, which is the filling factor here, and there is another filling factor inside there. Okay. So you have gates on both sides, and you can change the density as you wish. Okay, so now let's say that we do this experiment, we have 3 minus 0. So we have depletion and 3 in the center. Or we have 2 and 3 in the center. Or we have 1, okay? So every time you can see just a simple test, okay? That here you have 3 modes, 2 modes, 1 mode. And then you measure, I don't want to show you again, the same experiment that we did, that we started doing 4 hours ago. And you get here 3. And this is also the distance. So the distance is long again. It's 160 micron long. Did I mention it here? Is it written down here? I don't know it's written, but it's 160 micron long. So you see 3 minus 0 is 3 kappa naught, 2 kappa naught, and this is okay, right? This is the integer. And now I'm going now to 2 modes near the 5 half, 8 third and 7 third, which we measured before. Remember? Okay. So now we have 3 minus 8 third. Okay. So now we remove what is 3 minus 8 third? We have 1 third left. Okay. And now, if I measure now the conductance of this 1 third, okay, we measure something very close to 1. The thermal conductance, the kappa, is very close to 1. It's sort of testing before we go to the 5. And if I go now to 7 third, then the subtraction now is 2 third. Right? 3 minus 7 third is 2 third. The problematic 2 third. And we measure now the conductance, thermal conductance, supposed to be 0. But again, it's not. It's still about 0.3 or so. I don't know if I wrote the number here or not. Yeah, it's 0.37. Okay, so probably we need a huge equilibration to find out what it is. Okay, so this is the same as we did before, but we do it now in the 7th cell. And now we go to the 5 half. And we go to the 5 half, it's again the same story as before. Okay. we expect we have now an interface of 3 minus 5 half. So here is 3, and this is the 5 halves. And here you have, look at the direction. You have to remember by heart the direction, okay? So trust me that that's the way it looks like. And each line, this is a half charge, half conductance, so this is always a marijuana. So here in this antipathian, you have living a hot source, both of them are very hot. And they're equilibrated. You don't need to equilibrate. They're equilibrated because the distance is not very hot, it's 160, but they live hot and they remain hot, okay? And you basically measure 1.5 kappa 0, okay? Because it's 1.5. And if you go now to the pH Paphian, okay, then it's in opposite direction as usual. So this goes this way, so this one goes down here, okay? And then this guy, there is a hotspot here you don't see. I should have put in here hotspot, okay, of the marijuana comes from here, I'm sorry, and the charge comes from here. This comes hot and this is cold. And they equilibrate and you get half. So what you expect to get in these two experiments is supposed to get or the half or the 1.5. And you get half. Okay, so this is again, maybe you have to look at the paper again, look carefully on the arrows, etc. So we have this pH Paphian, and then we did also 2 minus 5 half, and we get also half. So all the experiments until we did until now is a pH Paphian. And what is left now to do is just to show you the very last one. Okay, and the last one is not measuring 2 terminal anymore, but is to measure now the kappa xy, the true topological order. So how do you do it? What is the topological order? How do you do it? Okay. So this is the 5 half and 7 half. To do it is actually to measure, like Kane and Fisher showed this picture. You say one goes this way and one goes this way, right? So you take this minus this. If you have 2/3, you have this one minus this. Okay, so the topological is subtracting or adding edge volts. Okay. Okay. So now you have here now the all effect around 7 half, nearly 0 here, and the 5 half here. Okay, so these are the two ones that we are going to measure. Okay, and the measurement now is going to be kxy, which is k down minus k up. Before we trusted the down minus up will equilibrate. We find this minus this, that is up. But here we are going to measure k down and k up separately. That's subtracting. Okay. So how do we do it? So we have now this more complicated device, short distance, no equilibration here. So for example, 2.5, you have 1, 2, half, and a -1, if it's a pH Paphian. Okay? So let's say it's a pH Paphian, okay? And then the same thing here now. So I put it hot, and all of them going from here to here. I'll measure now the down heat, okay? And then I heat up this one, and I measure the up heat. And that's subtract. Because if they are equilibrated here a little bit, they will equilibrate again here and it will be subtracted out. If there is also bulk, the bulk will be added in, and it will be also added in and subtracted out also. So the structure to do it really is a bit more complicated because you have to measure exactly, you have to measure, when you come here, you have to measure how much power is absorbed, for example. How do you know how much power is absorbed? You have to measure the temperature, etc., etc. Okay, so this is a complicated experiment. And the paper was published, you can look at it, okay? And then these are all the whole thing around the periphery of it that measures the temperatures, etc., etc. I don't want now to be another hour to talk about it only. So what you do, so when you test fill factor 2, okay? So you measure, this is downstream. For one, this is the downstream, okay? You can see the modes down here, and you can see the one mode down here. So this is 1 kappa 0, this is 2 kappa 0, this is 1 kappa 0. And now if you open it up totally through the bulk, there is nothing there. Okay? So we didn't find anything going back. I didn't show you. I should have shown something, nothing goes there. So the 2 is a 2 and the 1 is a 1. But now, let's go back to our beloved 2/3. We didn't never want to be kappa 0. So now we do exactly kappa xy. So this is really an SCM picture of the device itself, okay? The size is about 20 microns long, okay? And what we do, you measure now, all the power comes down, okay? P down, okay? And we get 0.45 kappa Z. And now we are reversing the heat and we measure everything that goes up. And now we subtract down minus half. And then we get something that is 0. Okay? So now this is 2/3 gives you a 0 kappa 0. And what we couldn't do before, now you see it. And the same thing now happened. I'm going to finish now. I'm not going to show you all this measurement. When you do now 5/2. So we measure now basically down minus half, and we subtract it, we get 2.5. But again, 2.5 expected, 2.5 kappa 0. Okay, and if you go now, this is a pH factor, and if you go to 7/2, there was no prediction to 7/2 at all. Basically, we do the same thing. Okay, so we have now again 4, before it was 3 minus this, we get 3.5. So this is the right, correct, and more complicated. I have 20 figures, to go into all the details, how do we actually measure all this stuff, okay? So this is also the pH Puffian-like for 7/2, and not 5/2. So I'm finishing now telling you that we made this 5 different experiments, 4 different, how many you count them. And the reason to do it, Sam, because if you look at I collected all the literature in this period of years. And you can read searching from the marijuana, hidden marijuana, after we publish. You keep writing review papers, etc. like this, that are still looking for the marijuana. Even though the pH Puffian, maybe you could say looking for the anti-Puffian, but looking for the marijuana, because we see half all the time. So we see M plus half. And they want to do M plus half, or whatever. Anyhow, so it took a few years, and many experiments, and about 6 students, give every time I left. Okay. So I want to show you after this transparency, this is sort of like the last one. And what I want to show you now is a paper that arrived now. Okay. So thermal transport in the department. And I heard another paper on the ICAR 2 weeks ago from Steve Simon. Remember the name Steve Simon? So I don't know if you can read it here, but let me tell you, this is a fantastic paper. Theo, could you read yourself? This is all the names of the guy, okay? But what he says here, if I can read here, pioneering thermal transport measurement, and you can get it, it's in our, okay, 2 weeks ago. Pioneering thermal transport measurement in the 2-electron gas in high magnetic field that demonstrated the quantized Hall effect, filling factor 5/2 as a thermal Hall conductance, okay, in a half integer multiple of this kappa 0. I just made a copy paste. It still doesn't say anything about pH factor. It's saying that it's just measuring. So the half integer is signature of neutral Majorana edge mode in turn linked to the presence of non-abelian anion excitation in the back. However, the experimentally observed value of kappa correspond to a pH Puffian state in tension with numerical studies which instead favor either Puffian or anti-Puffian. This is okay, it's true. Okay. And then the last paragraph, they write that a variety of mechanism has been invoked to explain the discrepancy, but have been either ruled out by further experiments, other experiments that we did, okay, or else involve fine-tuning, okay, building on density matrix. Now he talks about what they do, group, etc., etc. At the end, the paper that he talks about, we propose an alternative resolution of this puzzle involving an edge reconstruction solely involve the neutral Majorana sector of the COT. Okay, it talks about an edge reconstruction of the edges of the system. Such a Majorana edge reconstruction can screen the Puffian or the anti-Puffian bulk so that the transport signature becomes distinguishable from those of the pH path. When I got this paper, I got the same, I didn't say that. So he admits that we should have measured pH path here, okay, if you trust it. So his experiment, you know, the paper itself is highly theoretical paper. We say pH path. We argue that this physically natural scenario is consistent with the experiment. He was so much against that. Okay, so this was, I don't know what to say about it. This was a major experiment that we did all the time. It caused a lot of suffering. But one thing I want to say, that maybe I don't feel like saying it, but when I read 3 months ago the citation of the Wolf Prize that I got, they specifically say there whether the judges from there, that we have seen the marijuana a long time ago. They don't say pitch factor. We observed the marijuana. And this is one of the reasons that they gave the prize also. But this is less important. The important part is that if these papers, they do DMRG and stuff like this, that I'm not very good about it, that this something here made me happy. Thank you.
I guess I don't understand the last part. So is the bulk Pfaffian or anti-Pfaffian?
The bulk is Pfaffian or anti-Pfaffian. There are calculations that is this or that. They don't know. They say it's usually more anti-Pfaffian in calculation than Pfaffian. But the edge mode, if you read a little bit more into the paper, but the edge mode is super wide, and it basically depends how big is the bulk. It conquers the bulk. So every time that you measure something along the edge, you're going to see pH value. That's what he's saying.
Okay.
Thanks, Mark. That's very nice talk. So about the kappa XY part, you said it's kappa up minus kappa down. So do kappa up and kappa down themselves have meanings, like they should be expected to be quantized or not? Because
yeah, they are quantized.
But in the 5-half you showed, I see their difference is quantized to.
You mean because I measured 2.45 instead of 2.5 or something like this?
No,
That's what you mean?
that one is good, but kappa up and kappa up itself is not integer or half integer.
Well, it's okay. So the numbers that look, this is an experimental thing. It's expected to get duped. What is? Let me see. Explain to me more. I don't know what you mean by this.
Yeah.
The up and down is or even this one. It's 4 plus minus 0.5. This experiment. You measure noise. You measure this. Okay, this is 0.54. So you wanted to that I measure here exactly 0.5 instead of 0.54.
Yeah, this one looks close enough to.
And the other one is what's the difference? The other one is also it's okay. So there is some noise and some usually the paper and there is some error bars
So
in the
that's
paper.
noise, I'm saying.
No, yeah, there is uncertainty when you measure stuff.
Okay.
Are you experimentalist or theorist?
I'm not serious.
Okay, I understand what you're asking.
So it's more fast.
Thanks for the talk again. So I'd like to ask about maybe probably the first experiment that you did, and we discussed the test case scenario. You measured thermal hole for 4/7, 3/5, and then 2/3, and you argued and you showed results showing that the 2/3 does not equilibrate well. But for other cases, it seems to equilibrate very well.
Yeah.
In all three cases, you have counterpropagating edge modes. It's just that for the 2/3 case, the chirocentric charge happens to be exactly 0. So you expect to find 0. But can you explain a little bit more why it's so hard for 2/3 to equilibrate? Well, for other cases, we also have counterpropagating modes, but it seems to equilibrate.
Yeah, but there are there is one going back and around many versus one. Okay, and here it's 1 versus 1. They fight 1 versus 1. The 2/3 is down 1 and up 1. When you go to the other one, you have now something that goes down 2 edge modes going two neutral and 1 charge. Okay, the one that is -1. Okay, so why do this multiple mode equilibrate better than 2 only? I don't know. I don't know it. Dima Feldman and also Steve Simon calculated that each of them is like 3 or 4 papers talking about equilibration. It's not equilibration of charge. It's equilibration of temperature. Namely, you have photons basically going from one edge to another. Okay, there's no charge moving from one place to another. It's just energy move from one place to another. And why does it happen? So there is some cost capacitance or something like this. I don't know why multiple mode versus one equilibrate faster than 1 versus 1. I can't explain. I don't know. That's the experiment.
Can I ask another question? So about the very last experiment about kappa x1. So I guess kappa xy will be defined using a 4-terminal setup, but it's actually in your experiment measured in a 2-terminal way. Is that correct?
What do you mean 4-terminal?
So kind of like sigma xy or r xy is defining a 4-terminal.
Yeah, the kappa xy. Okay, the kappa xy basically in this particular case, in heat, you measure down minus half on the other side. Okay, you measure here minus this one on the other side. Okay, so this is that's exactly the kappa xy or the rxy. When you measure the Hall effect, you have current going here, and you want to measure vxy. Okay, so you here, and then you go ground, and here there is 0. You measure this minus 0. That's the same thing.
And does the effect of a hot spot and stuff affect your measurement or your interpretation?
In this particular case, there's no hot spot at all. There is a hot source, and current comes down and heats up the other contact. And then I calibrate how much power arrives there. How do I know it? I have another circuit there, and I put some power that raises the temperature to the same temperature that comes from the other side. You see what I mean? Suppose the temperature here went up by T. Otherwise, it's cold. So now I come up and I have a whole circuit on the other side, and I know how much power I drive into this flow, the other contact here. I say, oh, I put so many femtowatt, and I got the same temperature. So this is the same temperature they get from the other side. So there is a process of, and I mean, from here to here, we do the other side. We send from here to here, and we calibrate that. It's an involved experiment. If you want, if you don't want, look, I don't want to show you all these many transparencies here that talk about this. I'll show you just a little bit how the device looks like. Let me go fast. I didn't want to bother. You see, this is the structure. It's a complicated structure that each of these sides, I have calibration of the S and calibration of PM, and I have the amplifier here and amplifier there. It's a very complicated measurement. Okay? But the bottom line is down minus up. That's the kappa xy.
Thank you very much.
Just a general question, how difficult is it to generalize the thermal measurement to superconductors? Suppose you have topological superconductors.
I don't think the superconductor conducts heat.
Right, but there has been predictions. Yeah.
Okay, I don't know. It's a dirty superconductor, but we can sometimes put a superconductor because it doesn't want to have heat conduction. But I didn't think about it. If you want to see some residual heat conductance in superconductor, I don't know if this particular experiment, because this experiment has to do with edge modes. It's a Hall effect, okay? Superconductor, you have heat going maybe through the bulb. Yes, so I didn't think about it. Yeah.
Okay, so we'll stop here. Let's thank the speaker again.